Differentiate sine x, you get cos x. Right? That's the major relation between them. But what happens if you differentiate cosine x? You get negative sine x. These rules, like the ones we did before, the power rule and sum rule, you need to memorize these things. So derivative of sine is cos, and derivative of cosine is negative sine. Let us now figure out the other four. What other four functions do we have to worry about? Tan, and then the reciprocals. Cosecant, secant, and cotan, right? We need to know their derivatives. I want to know the derivative of tan x. All right? But all I know is the derivative of sine and cos. But tan is sine over cos. So if I want to know the derivative of tan, I should figure out the derivative of the quotient of sine and cos. We talked about the quotient rule yesterday. So how would the quotient rule look for this particular problem? The derivative of sine over cos.
Cosine times the derivative of sine x, which I guess is cosine.
Okay.
Cosine times cosine x minus sine times negative sine x
Good job, Justin.
over cosine x squared.
Sounds good. That sounds perfect. Oftentimes when you square or cube or raise powers of trig functions, you put the exponent on the function symbol. You don't write it outside in parentheses, right? Oh, you can. There's nothing wrong with that. This notation has been adopted. Okay, so let's simplify this. The top says cos squared plus sine squared ultimately, right? Cos squared plus sine squared. What's cos squared plus sine squared?
1.
1. Unity. So this is 1 over cos squared. But why have a fraction? I don't have to. I can write this as secant squared.
Wait, what'd you do?
I simplified using Pythagorean identity. This is cos squared plus sine squared.
Okay.
Cos squared plus sine squared is always 1.
Oh, okay.
1 over cos squared is the same as the reciprocal. So we have the reciprocal function secant. 1 over cos squared is the same as secant squared. So derivative of tan is secant squared. Not the most obvious thing in the world. So we now have our first two given. We derive the third one. Derivative of tan x is secant squared x. Now we need the derivative of the derivatives, the other three, cosecant, derivative of secant, and derivative of cotan. And we'll use this previous material to figure these out. So cosecant x is the same as 1 over sine. So if I do another quotient rule on this, although it's a very simple quotient, just 1 over something, but that is the way it's derived. So 1 over sine x, I would write sine times the derivative of 1, which is 0, minus 1 times the derivative of sine, which is cos, all over sine squared. Everybody agree? That's the quotient rule applied to that problem. All right? Sine x times 0 is 0, so I'm left with negative cos on sine squared. But there's a fancier way to write this without ratios. So I can write this as negative cos on sine times 1 over sine. What is cos on sine? Cotangent. So we have negative cotangent x times 1 over sine, which is cosecant x. So the derivative of cosecant, it has itself back in it, and it's negative cotan cosecant. That's the usual way it's written. Derivative of cosecant is negative cotan cosecant. Derivative of secant, play the same game. It's the derivative of 1 over cosine. So it's very similar to the last derivation. This should be the same as the bottom times the derivative of the top. So cos times 0 minus 1 times the derivative of cos. right? Minus the top times through the bottom. So that is a negative sign. over cosine squared. Same basic thing happens, except this time we get a positive sign. So we get sine x over cos squared, but I don't want the ratio, so I'll write it as sine x on cos times 1 over cos. Sine on cos is tan. 1 over cos is secant. So derivative of secant is secant tan.
Wait, where did the sign come from?
The derivative, right, this is bottom times derivative of the top minus top times derivative of the bottom.
Okay.
Do I go too fast?
So you can plug any value in for x in a circle, and that will give you a slope. Well, between 1 and -1, that will give you a slope anywhere you want.
Not even between -1 and 1. You can plug any value in here. I'm sorry. You can plug any x value you want in here.
Yeah.
That is not going to yield an asymptote for secant, and it will give you the slope of secant.
At that point, we figure out what the derivative is, and we just plug our values, like plug it into a calculator, what the x value will be, what the x is approaching.
Yes. Now, in a lot of these problems, they're going to give you special angles, like pi on 4, pi on 2, pi on 3, pi on 6, this kind of thing.
Honestly, we just have to figure out where -√2 over
Yeah.
something like that.
Yep, that's right. And that will give you the slope of that function over there, right? That's right. Cotan, the last one, is similar to the tan derivation. So d dx, again, all these are to be memorized, right? Otherwise, there's not much to do with these things. D dx cos on sine, and do a quotient rule on that, and we'll have the answer to the derivative of cotan. So bottom times derivative of the top minus top times derivative of the bottom over bottom squared. Okay, so the top says negative sine squared minus cosine squared. So if you factor off the negative, it will read negative sine squared plus cos squared on the other side over sine squared. Sine squared plus cos squared, again, is 1. So we have -1 on sine squared. We're using reciprocal functions, so we don't have to have ratios. We'll have negative cosecant squared x. That is the derivative of cotan. So these 6 are what you want to memorize. Okay? I show the derivation because there are some homework questions in the textbook that revolve around these kinds of things, and so there could be in the online homework as well, I don't know. Okay? But the 6 major results are here.